All right, so video just about the mole for stoichiometry. And hopefully you're watching this video, you have heard of a mole before, maybe this is a review for you. But if you've never heard of it, we'll talk about what it is and hopefully make it make sense for you, okay? So in a mole, we're talking about chemistry, right? Moles are a very important part of chemistry. It's like arguably the most important unit in chemistry. We use it all the time. Very, very, very helpful because it lets us work with chemical reactions in a way where we can actually measure things. Instead of saying one atom of this reacts with two atoms of that and makes one molecule of this, that's not practical, okay? Meaning, if I said to you, for example, like, let's say, hydrogen, right, H2 reacts with O2, right? This is going to yield H2O, right? You say, okay, hydrogen gas reacts with oxygen and gives me water, okay? You say, I got to balance it, right? Hopefully you watched this video, you've learned about balancing at some point. You say it's not balanced, right? I have too many oxygens on this side, so I better maybe double this, right? Oops, that doesn't look great. Let's try that again. Double this, right? And then that fixes the oxygens, and then I got to double this, right? Hopefully you're saying, I know why that works. But this means what? It means take two molecules of H2. Remember, H2, we could draw the Lewis structure, would look like this. That's an H2 molecule, two bonded hydrogen atoms, if it makes sense. So you're saying take two of them. Okay, so that's two. That's what the balance is telling me, two molecules of it. One molecule of O2. O2 is a Lewis structure, would look like this. I'll put the dots in, I might as well, right? Be consistent, good Lewis structures. So that's one molecule of O2. And we're going to produce two molecules of H2O, and H2O would look like this. So here's my first water molecule. Okay, that's one H2O. And then I can have my other one, right? Two molecules. That's what the coefficients mean. Okay. So hopefully, let's fix that a little bit. It doesn't look as nice as I wanted. Right, so two molecules of H2O. That's what this means. The problem, and the reason we need moles to fix this problem, the problem is that there's no machine probably in the universe, let alone Earth, that can measure individual atoms or individual molecules. They're just too small, okay? Like, atoms are insanely tiny, all right? Like, I mean, you say, well, they're small, sure, but I can probably see them. No. I mean, we're talking picometers. A picometer is a trillionth of a meter. So if you picture a meter as about 3 1/3 of a foot, it's a little bit more than a yard. A yard is not a yard is 3 feet, but it's not a meter. A meter is a little bit bigger. Okay, if you imagine taking that meter and dividing it into a trillion little pieces, right? You can understand how small atoms are. It's insanely, basically impossible to measure them individually. So you can't measure individuals. That's just not possible. But what you could do is maybe pick a bigger unit for this. AKA, if I said, for example, instead of two molecules, let me switch colors here. What if I said, hey, this is 2 dozen, right? So when I put a 2 here, what I really mean is dozen. Okay, let's just say I pick that because, we all know a dozen. Well, that means what? 2 dozen would mean 24 molecules of H2, right? 1 dozen O2s would be 12 O2 molecules, and so on and so forth, right? You might say, well, that fixes it. Well, it's better, but we're still way off, right? We still are not even close to being able to measure this. So a dozen is just not going to be big enough, okay? So we take that dozen and say, not big enough, all right? What we do instead, and maybe you're seeing where this is going, is we say 2 moles, okay? 2 moles of a substance. And a mole, to make it very simple, is basically, I'm going to type it out, type a little bit faster than I can write, if that makes sense. A mole can be thought of in a couple ways. To start out, I want you to think about it as basically, let's make this a little bigger. This is basically a big version of a dozen. Okay, so I'm going to say basically a giant version of a dozen. Okay, So when you see a mole, I want you to think about it as I could have a mole of anything. I could have a mole of hydrogen, sure. I could have a mole of computers. I could have a mole of water bottles. I could have a mole of hairs. I could have a mole of sweaters, whatever. It doesn't make a difference, right? It's basically a dozen. So if I say a mole, you and I would say, I know what that is. That's a specific number. What is the specific number? The specific number, it's very specific, is, let me switch back to drawing, I guess, oops, let's switch back to this. Sorry, there we go. A mole of anything, I don't care what the substance is 6.022 times 10 to the 23rd. Okay, of anything. Again, could be hair, sweaters, jackets, atoms. It doesn't make a difference. You don't usually use this for anything outside of chemistry, though, right? It's kind of silly to use moles if you're not talking about something in chemistry. Okay, it's a very big number. Okay, 6.022 times 10 to the 23rd. I mean, to give you a comparison, that would be nearly a trillion. So if I gave you $1 trillion, that's a lot of money. If I wanted to give you that amount of dollars, I would have to give you that amount of money, that $1 trillion, roughly 1 trillion more times. Like I would have to give, here's $1 trillion, and then do that 1 trillion times. That's how big that number is. Okay. Now, technically, what I'm giving you here is the number 10 to the 24th, right? That is 1 trillion. And if you're saying how does that work, this is 10 to the 12th times 10 to the 12th, 1 trillion. That's what it means. So this number is not exactly that, right? But it's close. Technically, it's off by quite a lot, actually. But for visualization purposes, it kind of works, okay? And guess what? I can measure a mole of something. So this is why we do it, okay? We don't just pick this number because, hey, it's funny. We pick this number because it's very helpful to us. So let me erase all this. Oh, that's not what I wanted. That's not what I wanted, man. There we go. Look at that big eraser. Okay, and again, if you need to rewind the video to get, obviously you can do that, right? If you're like, hey, I didn't have that then, I don't have that written down, rewind the video. Okay, so a mole can be measured. You say, how? What machine measures moles? Well, it's not that a machine does it, it's that we use a mass balance. I would put my sample of whatever it is, whether it's hydrogen gas, maybe in a balloon, maybe it's water in a beaker, right? And guess what? 1 mole of, let's say, we were doing hydrogen, right? So, let's make it a little bit simpler to start. Let's pick, say, lithium, okay? Or let's do helium. Helium is good. 1 mole of helium. Okay. Oops, can I spell maybe helium? I think that's right. I can't spell to save my life. 1 mole of helium is, guess how many grams? It's approximately 4. It's like 3.9. Let me check my periodic table. I don't have it memorized. Oh, no, it is 4.002602. I thought it was a little bit less, but I guess that makes sense. Is 4.002602. Okay, a very specific number. And you might say, well, that's the mass of it. I mean, that's how much 1 atom of helium is. On average, is about 4 AMUs. But now we're worrying about moles, which means if I have 1 mole of helium, that means I have 6.022 times 10 to the 23rd atoms of helium. Imagine I have all those atoms collected in, say, a balloon or something like that. That would have a mass of only 4.002602 grams, which is not that much. Okay, that's like 4 paper clips. That's pretty light. Okay, and this should really sell to you how small atoms are. To have that many atoms only have that much mass is kind of crazy if you think about it, right? You're like, that's a big, big number. Yep, but atoms are so darn small, even having that many of them still doesn't add up to that much mass. But the beautiful thing is that this number here, I can put that on a mass balance. Let me try that again. I kind of, oops, no, not that. No, not that. Stop. There we go. Sort of. This number right here, I can measure that. I can put that on a mass balance, right? And say, hey, that many grams. If it's helium, if every last atom was helium, it would be that many grams. Okay. What about, let's say, the next element would be lithium, right? So 1 mole of lithium By the way, MOL is the abbreviation we use for mole because in chemistry, writing 4 letters is just too much work. So we do 3 letters. 1 mole of lithium, of Li, is going to be approximately 7. It's like 6.9 something. Let's see. 6.941. Okay. This would be 6.941 grams. Okay. Oops, that looks like a 4. 941 grams. Which means if I had a mole of lithium, it would have a mass of 6.941. I could measure it on the mass balance. I could put that piece of lithium metal on the mass balance, and if I have that many grams, I have, in theory, exactly 6.022 times 10 to the 23rd atoms of lithium. Okay? The reason this is useful is because the idea of saying, let's go back to our hydrogen, right? H2 plus O2. All right, we'll balance it. This concept where I can't do dozen isn't enough. I can't do hundreds. I can't do, millions or some unit that I make up. I would use moles. I could measure that. I could say 2 moles of hydrogen reacts with 1 mole of oxygen to give me 2 moles of water. Okay, because I can measure the molar mass of all those numbers. He's saying molar mass, what's that? I'll show you, right? Molar mass, we've already been doing it, but just to kind of put a word to it. Ooh, that noise, that scratching noise, I'm not a fan of it. Molar mass, so let me change the side a little too big, I think. There we go, maybe that's better. Yeah, that's better. Molar mass. This is simply the mass. Oops, oh, let's try that again. No, not that. No, not that. There we go. Molar mass is the mass of 1 mole of a substance. Notice I say a substance. It could be a element. It could be a compound. I suppose you could do a mixture too, but that would be kind of messy. Okay, so basically 1 mole means I have 6.022 molecules of that. So I can write it like this: 6.022 times 10 to the 23rd. We'll just say molecules. It could be atoms as well, but that's fine. Molecules is equal to 1 mole, which is equal to 1 molar mass of that substance. Okay, so we pick maybe another element. Maybe I pick, I don't know, uranium, right? So if I have 1 mole of uranium on the periodic table, according to this, is 238.02, and then 891 grams. Notice how much heavier that is, right? That's appreciable. That's that's actually a little bit below a quarter of a kilogram, which, is like a little bit less than a pound, like half a pound roughly. Okay, so you could feel it in your hand and say, oh, okay, that has some weight to it. Okay, there'd be 6.022 times 10 to the 23rd atoms of uranium in that sample. Okay, that's a mole of uranium. And one thing we should do with the molar mass when we write it is the unit is always grams per mole. Okay, because this is now a conversion factor. I can use this to convert between grams of uranium and moles of uranium, okay, which is very important for us. It's going to be very important for us, okay? So I don't care what substance it is, it would look like this, okay? To prove that, let's see, can I, oops, yeah, this works. Look at that, fancy. Perfect, all right, using this writing tablet for fun. So back to our reaction, we had H2. We had 2 H2s reacting with 1 mole of O2 is going to yield 2 moles of H2O. I can find the molar mass of each of these substances. So for H2, how do I find the molar mass? You're tempted right now, I bet, to just say, oh, it's 1, because on the periodic table, hydrogen is about 1. It's 1.008, if I remember correctly. 1.00794. Okay, very close. So what you do here is you say, the mass of hydrogen is 1. That's not what I wanted. 1.00, what did I say, 794? Is that what I said? I think that's what I said, yeah. 794. You say, okay, that's the answer, but there's two of them. It's H2. There's two of these atoms together, which means I have to multiply this by 2. And that's going to give me what? 2 point, if I can do this math in my head, let's see, 0, 1, oh no, I don't want to do math right now. Yeah, I'll just do it. I probably shouldn't make educational videos and then not do the education. That's probably a bad idea. 1.00794 times 2 gives me 2.01588 grams per mole, which means if I have a mole of H2 gas, hydrogen gas, I would have to have that many grams. And if you're like, but why is it 2? I still don't get it. Because it's H2. It's not just H. It's not hydrogen by itself. That doesn't exist. It's H2. 2 hydrogens bonded, which means I need to incorporate both atoms. It's like a pair, basically. Okay. So that's hydrogen. And then I can do the same thing for O2. Okay. So now I need oxygen's molar mass. Oxygen's molar mass, again, you're going to find these all on the periodic table. It's almost like there's a reason we put these in every science classroom in the world. They're very helpful. Oxygen is going to be about 16, 15.9994. Very close to 16, 15.9994. Hopefully you're saying, oh, there's a 2 there. Does that mean I got to? Yup, it means you got to double it. And this is going to give me, so 15.9994 times 2, 31.9988 grams per mole. Which means, again, if I have a mole of oxygen gas, O2, it has to be that many grams, about 32 grams, 31.9988. And then lastly, H2O. Now this one you might say, oh, it's a little bit different. It is, but it's not that bad. What I would do if I were you is do them one at a time. So I have H2, I have hydrogen, and I have oxygen, right? I have 2 hydrogens, and I have 1 oxygen. By the way you do this, the order's up to you. Multiplication, 2 times 1 is 1 times 2, right? It doesn't matter which one you put first, right? 2 times 1.00794. Hey, we already have that. That's the 2.01588. Right? And then for the oxygen, this is 1 times 15.994. Hey, that's the same number, 15.999, 4. And you say, okay, what do I do with those numbers? Well, they're all together, right? 2 hydrogens, 1 oxygen bonded together, which means I better take these numbers, these molar masses, and add them together. And what do I get? Well, let's find out. It's going to be about 18, right? But let's see. 9994 plus 1.000, or no, 00794, and I get, oh, I'm sorry, what am I doing? No, 2.0. Ah, here I am being silly. 15.9994 plus 2.01588, and I get 18.01528. So 18.01528 grams per mole. Okay, so I have my 3 numbers here. Of course, I'm like writing all of them on accident, and these numbers correspond to what? This is the molar mass of H2. This is the molar mass of O2. This is the molar mass of H2O. Okay, so that's what you would have to figure out, is the molar mass of each one of these substances. And then, this, as you can imagine, this video could go on and on and on and on and on and on. There's a lot more stuff to learn about this. But hopefully you're saying, I kind of know what a mole is, okay? It's a way of basically taking into account the fact that atoms are very tiny and you need a big number of them in order to actually measure them, okay? If that makes sense. All right, so hopefully you're saying, okay, I kind of got that. And hopefully you make sense of how to get the molar mass, which again is just using the periodic table and making sure you know what substance you're working with. Okay, so we'll call it quits for here. Hopefully this helped, and hopefully you are ready for the next step of chemistry. Right? Awesome. Well, you have a great rest of your day, and I'll see you in the next video.